So we're looking at an electric motor, and the first one we're going to look at is a DC motor. And the DC motor has input current, DC current. Okay, so I'm going to draw the brushes on here. Brushes makes contact with the coil. So here we have a brush that makes contact with the coil, and let's say we have our positive terminal, negative terminal of a battery there. So in which direction is the current flowing here? From the positive. It's flowing from the positive. So the current will be flowing. The current will come in here. It will go here and it will flow there. So the current there through that part is in that direction. Am I right? You're following? And then the current flows around the loop and it comes through this part, and this is my conductor, sorry for the and it goes there and it goes in there back to the cell. So because the current is flowing down there, up there, this current carrying coil will experience a force. In which direction will it experience a force? So let's say this part of the loop is A and that part of the loop is B. Okay. So which rule do we use? Number one. The Fleming's left hand motor rule is what we will use. Okay. So what we do is our middle finger must always follow the current. Our index finger must follow the magnetic field, which will be from north to south. Then this part of the loop will experience a force down. And this part of the loop will experience a force up. So this loop is going to turn clockwise. But when the loop gets into the vertical position, the brushes are on the gap there in the split ring commutator. So there will be no current flowing when it's turned to the horizontal position. The current, so this is the direction of rotation. It is anti-clockwise. Okay? In the vertical position there's no current, but because it was busy turning, what will happen? It will flip over. Can you see when it flips over, the brushes on the left hand side is making contact with the orange part now, and the brush on the right hand side is making contact with the yellow part. So what will the direction of the force be? Now A and B has swapped positions. You just swap A and B's positions. So this is now B and that is now A. Can you see that the split ring commutator has now caused the current to flow in that direction through B? When it was on this side, it was coming down. On that side, it's going up through B part. Okay? So what's the force on the B part now? Down, and the force on the A part will be up. Is it clearer? So the moment it goes through the vertical position, then no current will flow because the brushes will touch the gap of the split ring commutator. Okay? So a DC motor has a split ring commutator, and the input is electricity, the output is mechanical energy. Okay? So now we're going to go to the AC motor. Okay, so we'll call the yellow part, this is now going to be an AC motor. So what is the input energy? Alternating current. So the brushes are touching that part that is connected to B there, and this part will have an alternating current flowing through it, and this brush will always touch the A part. So our input is electricity, we want output mechanical energy. Okay? So during one cycle we can say, I'm going to choose a direction for current now. I'm going to say the current in the circuit is flowing in this direction now. So it is going, it's touching this yellow, and there's a stick that goes to the yellow. It's running through that orange. So here, the current is coming up through A, it goes around, and it comes down through B, and B is touching this slip ring. So the current, for one rotation, the current is flowing in this direction. Okay, so what's the direction that it's going to turn in? The rotation will be, now don't guess it. You've got much to remember. So don't guess clockwise or anti-clockwise. Figure it out using your left hand motor rule. So finger, index points north-south, current points up through A. So part A will turn down, part B will turn up. So it's going to turn anti-clockwise again. Can you see, when it reaches this part, the current must be 0 in the coil. Why must the current be 0 in the coil? There is no current, because we're working with alternating current, and alternating current will drop to 0. Every 90 degrees turn, the current drops to 0. Then the current will flow in the opposite direction. So what's the opposite direction now? The opposite direction means here. The moment it turns over, momentum makes it turn over. Now the current is going to flow in this direction, and this part of the brush is touching this orange. And in which direction is the current flowing? It's flowing up here, but this is now B because it's flipped over. I know how to solve that problem now. So the part there will come out, it goes under in there, and it comes out there. So the current has now flipped around through the external coil, but because I'm using slip rings, the current flows in the same direction through the loop. Can you see that? Okay? So I just want to sort out something here. Just want to sort. Are you happy? Okay. So that's why, because of the slip rings with AC, you'll have the current flowing through the loop in the same direction. So it will carry on turning in the same direction. But through the external circuit, the current, every 180 degrees, the current swaps direction through the AC circuit. The first time I looked at it, the current was flowing in there. Now I look at it and the current is flowing out from there. Are you okay? Okay. Let's look at the dynamo or the generator. And because it's easier to work with the AC, I'm going to do the AC generator first. And that's where we ended yesterday, am I right? The alternating current generator. Okay, so what is the input here with the generator? Mechanical energy. What is the output energy? So somewhere here, somebody is turning this thing. And here, linked to the coil, you have a galvanometer or an external circuit that will measure current. You don't have a battery in a generator. The generator is the thing that creates electricity. So I'm going to turn the coil so that it will turn clockwise. This is the rotation. It's going to turn clockwise. So A is going to move up and B is going to move down. We've got the slip ring here is B's slip ring, that slip ring is A's slip ring. So if A moves up, in which direction is current flowing through it? If A is busy moving up, in which direction is current moving through it? So we use, to figure it out, we use the right-hand dynamo rule. So here I don't know what the direction of the current is, but the thumb must point up if A part is coming up towards me. The magnetic field is from north to south. So the current that is created in A is going to flow up. So current here will go up. And obviously it follows the loop here, so it's going to go down B. The current is going to go down B. Now let's follow what happens in the external circuit. So the current comes, it flows through here, and this commutator, slip ring commutator, is receiving this current that comes through here. So this voltmeter or galvanometer will deflect in this direction. Are you following me? And it goes out underneath there and it comes out there. So if this thing is turning clockwise, while A is on the left hand side, the current will go up, while B is on the right hand side, the current will go down. And while it's moving through that horizontal position, the current that is created is a maximum. So if I start there, then the current is a maximum. So it's going to go from there to the vertical position, it turns 90 degrees. If it turns 90 degrees, it reaches this place where there will be no current flowing because of the motion of the coil parallel to the magnetic field. There won't be any current flowing there. So what now? Now I keep turning it, and what's happening? So that needle there will drop down to 0. It will have no reading. In the vertical position, it's got no reading. So it's a 0 reading there. Now I turn it. I'm busy turning it clockwise. While it's moving clockwise and it's going from the vertical position into the horizontal position, What is happening? In which direction is the current flowing? Okay. Whose rule must I use? Dynamo. Fleming's right hand dynamo rule. So, B is busy moving up, am I right? Yes. Up, thumb up. Magnetic field is busy from north to south, so in which direction is the current in B? It's coming up in B and down in A, but now the slip rings have changed. So A's slip ring goes under there, and here the yellow one is A's. So it will touch, it will now flow in that direction. Can you see that the current, the needle will now deflect in the opposite direction? Okay. So although it looks like the current is flowing in the same direction through the coil, through the external circuit, it's flowing in the opposite direction. So while this thing is turning like that to the horizontal position, the current will increase to a maximum. The moment it reaches the horizontal position, the current is a maximum. Carry on turning it, what happens to the current? It decreases to a minimum. So after 180 degrees, the current is a maximum but in the opposite direction, and then it decreases to a 0 again when it's in the vertical position. And if you turn and turn and turn, after a 360 degree turn, you'll have this shape current. If the loop started in the vertical position, then the graph will start at the 0, and then the graph will look like that. So after 90 degrees turn, it will be a maximum from 0 to a maximum. There, if the loop starts in the horizontal position, the current starts at the maximum. But the graph's telling us the same thing. After 270 degrees, the current will be a maximum, and after 360 degrees, the current will be 0 again. Happy? Lovely. So this is a current and time graph or cycle. Time or cycle graph. Let's start the coil. Let's start this coil in the vertical position, because that is the position where the current will be 0 as you rotate the current. Okay? So I've got brushes here that if the coil is in the vertical position, the brush will short the coil. The current will not flow through the coil or the loop or the armature, whatever you want to call it. There is no battery in this circuit, so it is, you can have a device like a galvanometer attached to the coil. I didn't put all the other things in. I've just got a galvanometer there that will indicate the direction of the current flowing. So I'm going to deliberately rotate the coil clockwise. So this is the direction of rotation. And in the vertical position, the current in this coil is 0. So the current is 0 in the vertical position. What's happening in A as it is moving in that direction? What is happening to B as it's moved in that direction? So that's the big question we have to ask now. How can we find out what's happening? It's a conductor, that is moving in a magnetic field. So what is happening? How am I going to find out what is happening? We use Fleming's right-hand dynamo rule, where I want to find out where what the current is doing. So I know that A is moving down. The magnetic field is from north to south. A is moving down. So what's the height? You see how difficult it can be. So the current is pointing towards me. Am I right? Okay. It's easier to. So A is moving down. My thumb must point down. My index finger must point from north to south. So my middle finger is going to point in the direction of current flow through A. Maybe it would have been easier if I looked at the current that's coming in through B. So where's our green? So current, while this loop is turning clockwise, the current in A is down. Huh? So it comes down here. That is the connection with this split ring here, this half, and the current flows in this direction through the galvanometer. So in which direction is it going to go into B? Obviously up. Maybe it would have been easier to look at what the current is doing in B with my hands and twisting my hands. So this current will increase as it moves to the horizontal position. So because the cut in the magnetic flux is increasing. So by the time we get to the 90-degree angle, from vertical, where it's 0, to horizontal, it will be a maximum current. And then it carries on turning, and the current will carry on flowing in that direction. But as it goes to the horizontal position again, the current will drop to a 0. So now there will be no current in the coil, and no current in the external circuit the moment it reaches the vertical position. But something is busy turning this thing. So what is the direction of the current the moment it flips over? Okay, so A is busy moving up. What will the direction through A be? Okay, so it's Fleming's right-hand dynamo rule, north-south like that. B is busy moving up, so in which direction, A is busy moving up, so in which direction is the current flowing through A? Up. So look at what happens if I follow the conductor. So current goes up there and across and down here and out here through this commutator. Is the direction of the arrows through the external circuit changing? Wasn't it clockwise just now? Must I go back? Okay, so take B back to where it was. So B is busy moving up here. The current was going down through A, am I right? In this position, the current, as it turned clockwise, current was down A and up B, right? Yes, ma'am? Sleeping, ma'am?
Yes, ma'am.
Masitete should have encouraged you. So, down A, down A, down that yellow part, things shifted a bit. So can you see, while A was busy moving down, the current through the galvanometer was from right to left. And the current through here was up there. Can you see it? Okay, so through the galvanometer, the current, that external circuit, the current was flowing clockwise, as this thing is turning clockwise. Now, they're going to reach the place of zero current again. In the vertical position, there's no current. So I've graphed it there. In my graph, I've got the first 180 degrees. You got it? That's 180 degrees rotation. From that position to that position, the current went stronger and came down to zero again. Yes, ma'am? Okay. Now, remember, something is turning this thing. It's mechanical energy to electrical energy. So something is turning it so that it carries on turning clockwise. So in which direction is the current flowing through A now? It was down A. What is it now? Up A. And down B. Okay? So it's getting stronger. But what is it doing here? In which direction is it going through the load circuit? Can you see? It's going clockwise again. So it comes in through the brush there, and there we are. So it's going clockwise again. So the graph here increases to a maximum like that. And as you complete the rotation, it goes down through to 360, it will go down to zero again. Now A is where it started initially. Are you with me? So that's 270 degrees. Every 90 degrees the current will be a maximum.